background.
Thanks.
New, you think?
What's up?
New, is it new?
It's the same background as the end of my videos, but I just moved the URL to the top left. But yeah, how are you?
I'm feeling good after the score yesterday.
Yeah, yeah, you killed it.
So happy about that.
What did you do for the cars?
Well, it was Jack Weston, so
Got it.
yeah,
Oh yeah, you.
I do better on Jack Weston, so which was the other way around, but um I'm still doing AMC. Like I do a passage every day for AMC,
Yep.
but for this I use Jack Weston. Yeah, the bio was like um also yeah, at the bottom I write like under the table I write what I did for cars too. Um if you see it, I'm just gonna keep updating that.
Yeah.
But yeah, and for bio, I got a 128, which was like great.
Hmm.
I was really happy about that. I think one of the reasons though is because it didn't have as much genetics, which always like trips me up. So yeah, today I wanted to go over actually CP passages because there was one that I got 1 out of 5 on, and that I got 2 out of 5. So it's like if I do well on those, I would have gotten like 129 on CP, you know? So it's like it's just annoying when you have like those two really bad passages.
Yeah, totally.
So yeah. Also, one more thing. So like on your calendar, um, it's not a mistake, right? That like everything is open for like the next 3 months.
Yeah, yeah, yeah. So, yeah, because someone was asking me about like availability, like kind of down the line, because MCAT season's starting to pick up, um. Like I usually have like people schedule like a week in advance, but like now I have like my next 2 weeks booked, and then the third week like partially booked. So yeah, so I changed it so that you can schedule stuff like way down the line. And I also opened up Sundays as well.
Wow. No break, no time off.
Uh, like later on Sunday, like
Yeah.
first appointment for Sundays and Saturdays, as you know, you've probably seen with Saturdays is like I think 3 p.m.
Okay.
So,
All
yep.
right, good. So maybe I'll just sit down one day and just like schedule it all out.
Yep.
All right. You able to see it?
Hmm.
Okay. All
Uh,
right. So yeah, first one is physics pattern.
okay.
Muscular fitness can be quantified in terms of muscle strength and power. One group of researchers explored variance in grip strength to see if this simple test could be used as a reliable predictor of overall muscular fitness. This study was conducted among 438 men and women, ages 19 to 72. Hand grip strength of the dominant hand was used to assess upper body muscular fitness.
I'm really fast at noticing typos like instantly, and I just saw that.
Yeah, I saw that as well, actually. I saw that when I was taking the exam.
Yep. Yep.
Each participant was seated in the upright position with his or her arm along the side. The arm was bent at 90 degrees at the elbow, and the forearm and wrist in neutral position. Um, so would this be like this? You know what I mean?
Sorry. Let's see.
Like like that, the first sentence.
Seated in the upright with his or her arm along the side. The arm was bent at 90 degrees at the elbow, and the forearm and wrist in the neutral position. Squeeze. Wait, they're seated upright, arms bent 90. So like this. right? And then held the thing and they squeezed like that.
Okay. Each participant was given 3 attempts and the largest value was retained. Force measurements were recorded in units of kg, where a kg value is the equivalent force of the weight of a 1 kilogram mass. The results for grip strength tests on men and women were plotted in figure 1. Okay.
Let me see that up again. So sorry. All right. For some reason they're using kilograms for force. Um, but what they mean is, I guess, whatever, Newton and stuff. So, okay. And then we see this stuff, and we see kind of like this, kind of downward thing. All right. And then let's go down. Um, Similar downward thing here. Uh, it seems like, but overall thing is shifted lower, so overall grip strength for the women is lower, um, by like 20 roughly. But yeah, okay, cool.
Okay. Same participants were seated in a manner identical to trial 1, given the same diameter. However, this time electrodes were placed on the forearm to monitor muscle fatigue. Participants were instructed to squeeze the dynamometer, whatever, as hard as they could, and then hold it in the squeeze position until instructed to release it. Okay. Study administrator did not give instructions to release the dynamometer, allowing the point of muscle fatigue to be measured. A
Oh,
gra
failure,
yeah,
muscle failure.
muscle failure to be measured. Um, a graph of the results from the strongest female participant is shown in figure 2. Okay.
Okay, so this seems um like the squeezing happened here, and it's held for that time, and then they let go there, right?
Hmm.
Okay.
Okay. That's it.
Mhm.
So Newton's second law can be used to relate force to mass and acceleration. In trial 2, between seconds 8.5 and 33, okay, the diameter does not accelerate because A, the behavior of springs is not explained by Newton's second law. Um, Newton's second law.
What can you tell me about Newton's second law?
That something about is it I mean, trying to remember which one is which, but like,
It's the one that relates these.
oh yeah, F equals ma.
Now, people usually say that. It's a little uh there's it's a little bit there's a something, it's not just F equals like, tell me a little bit more about the F part.
Yeah, the like something is in motion, stays in motion unless acted upon by force.
Oh yeah, so that's Newton's first law.
Um,
Same thing. I mean, it's okay. It's not, uh but basically though, F equals ma is what people like typically remember, but really, or how about this? If I have FG here, FB here, which F do I use for F equals ma?
um, F of G.
Why?
because that's like the gravity is the acceleration.
Okay. But I mean,
It's our weight.
if you didn't have that, so the answer is use all of the forces. So it's really, the sigma symbol.
Yeah.
So it's really the sum of all the forces, which can give you your net force is equal to ma. Okay.
Hmm.
So so that's Newton's second law. All right, what do you think about choice A?
Behavior of springs is not explained by Newton's second law. Um, this doesn't have anything to do about springs, right? Or like, does it?
Yeah, I mean, I didn't see, I mean, maybe the diameter involves springs or whatever, but like let's say they did talk about springs. What would you still think about A?
Uh, it could be explained.
Yeah. Newton's second law, is any and every force, right? So it doesn't matter if it's a spring or not, right?
Mhm.
So that's out. And then we have B. What do you think about that?
So I was a little confused about what non-variable meant
Hmm.
during my exam. Like, does that just mean different forces? Like, there's variable forces. That means there's like different types of forces.
So what would the opposite of variable be? Like what word?
Just like I don't know about the exact word, but like
Like in math.
specific.
Like in math.
I can't tell. I haven't taken math in like 4 years.
Like so let's say we have this,
Mhm.
right? So these could be variables.
Constant.
Yeah, good. So okay, so B is saying that it only applies to constant forces. Uh but
Okay.
but yeah, there's nothing that says that it only applies to constant forces, right?
Right. And I mean, why is that? Like, so the forces can be like changing, right?
Mm-hmm. Um yeah. Because you can have um let's say uh I mean, let's say that we have something with a force going this way, and that force causes this to accelerate in this direction, which means the velocity increases in this direction. And if there's friction, the frictional force increases as velocity increases. So frictional force can be considered a variable force. It can move. I mean, it can change. But yeah,
Okay.
Newton's second law, nothing states that, it's only for constant forces, right?
Mhm.
Okay. And what do you think about C?
Okay. So it describes only unbalanced forces. That's probably um not true
Okay. Tell me.
because like if something is accelerating, that means that there's no net force. Like
You're saying if an acceleration happens, there's no net force here?
what I'm saying is like I mean two forces can like one can overpower the other.
Uh-huh.
So like yeah, I mean that means that oh wait, but well, there's can also be balance forces though. So like if
So
something is in equilibrium,
Uh-huh.
then those are balanced forces. But Newton's second law can still describe that.
So, uh, let's see, right? Uh, so for this object, which is submerged in water, right? It's the sum of the forces will be like Fg minus like Fb is equal to Ma, right?
Hmm.
I mean, you could do it the other way around. You could do Fb minus Fg, but they're in opposite directions, which is why we have different signs, right?
Okay.
Now, if Fb was equal to Fg, what would your acceleration be?
Yeah.
Mm-hmm. So that would be if they were balanced forces, right?
Okay.
So, but Newton's second law checks for the net force, meaning unbalanced forces.
But an F of net can be zero. No?
Well, F of net can be zero, but if F net is zero, acceleration is zero, right? And they're asking why is the like according to Newton's second law, right? Why is uh why does this not have an acceleration? It says not accelerate, meaning why does it have a zero acceleration value? And the reason it would have a zero acceleration value, right, is because the net force would be um zero, which would happen if you had balanced forces. And that can't explain it, but Newton's second law describing, like that relationship happens if you have unbalanced forces. Because then you sorry, so basically if Fg is equal to Fb, then F equals Ma would just be F equals zero. And thus, Newton's second law can't really be used here, right?
Yeah.
But let's say Fg is greater than Fb, your F net is going to be, positive, and your acceleration will be positive, right? So they're just asking, according to Newton's second law, why does like this situation have an acceleration of zero? And if you have an acceleration of zero, your net force is zero, but Newton's second law applies if your net force is not zero, because then you have that acceleration term as a non-zero value.
And wait, why would D be wrong too?
Um, so I mean, D is talking about the third law, and let's see, the diameter, I mean, sorry, the diameter uh, pushes back on the subject's hand with an equal. So, I mean, that's a true statement, but it doesn't have anything to do with Newton's second law, which is in the question stem, right?
Yeah.
Um, and also, Newton's third law doesn't really tell you much about acceleration, being zero, right?
Mhm.
Yep.
Okay.
So, so the key takeaway here is that Newton's second law is sum of all forces, aka net force, is equal to ma, and your net force, in order for it to be a non-zero value, you cannot have the forces being balanced. They must be unbalanced.
Mhm.
Yep. Okay. So this is just the definition that, you know, that they gave, right?
Yeah, I mean, this is like, is it just C?
Let's see. So this 1 kilogram value is equal to the weight of the 1 kilogram mass using G. So it's 1 kilogram times the 9.8 to give you a, yeah, 9.8 newtons. Yep.
All right. Well, it's the only one I got right. Yeah, at least it's something. All right. So next is this.
All right.
Many, hmm?
Oh yeah, just all right.
Yep, many dynamometers employ a spring to provide resistance as grip strength is assessed. If the dynamometer measures a force of 500 newtons after the spring is compressed 4 centimeters, how much potential energy is stored in the system?
All right. Formula time.
Yeah, so I know the formula 1/2 kx squared.
What's that
It's
for?
like spring potential energy.
Good. Anything else?
Um, uh, I mean, trying to think. Yeah, I know the normal potential energy is mgh.
That'll be gravitational potential energy.
Oh, okay.
But
Um,
but what about, something even simpler than energy, like force?
yeah, it's I guess ma.
Well, that would be the Newton's second law, uh but if there's, a distinct formula for the spring potential energy, there should be a distinct like kind of formula for the force of a spring, right?
Mhm. This is negative kx.
Yep.
Uh-huh.
So, and also, if you try to answer this question with the potential energy formula, we don't have the K value, right?
Mhm.
So but we're given force, so we can use the force of the elastic spring to find the K, because we have the X also, right?
Yeah.
Hmm.
So, okay, so basically we just have to do 500 equals negative k times 4 times 10 to negative 2.
Hmm.
Um, and yeah, I mean, we'll get 12,500, I think.
Hmm.
And yeah, the answer ends up being 10.
Well, so then you take the value that you got, the 12,500, and you plug it in for the K, right?
And then square the 0.04
What would
or
that
like, I don't know, I just use a calculator.
Wait, don't stop. Don't ever do that. Don't do that. No more like for the entire from now until your exam, don't
Okay. No,
even.
no, no. I never ever do. I'm just saying like just now I did. Just like speed up time. But yeah, I never use a calculator on the exams, of course.
Yeah, but I would say just stay away from it until
Got it.
after your exam.
Got it.
Because yeah.
Okay. All right. So 1/2 times 12,500 times 4 times 10 to negative 2 squared. Uh, well, okay. It would be 16 times 10 to negative 4. 16 divided by 2, 8. 8 times 12,500 times 10 to negative 4. Um, it would basically be 8 times 1.25. which is 10. Yeah.
So check out what I did.
Okay.
I'll show you. So this is that, and this is this. I'm going to rearrange K is equal to this. And I'm going to plug that in for K, 1/2 force over X times X squared. The X's cancel, so it's 1/2 500, which I'll say is 5e2. X, I don't even have to square it anymore. 4e negative 2. So this is 20e, well, 20, just that, times 1/2 is 10.
Nice.
Always do it like without the calculator. And if you can, you don't have to, but if you can rearrange it algebraically first, um, then that can help with the math.
Yeah. Yeah.
Mhm.
That's you always say that. I just sometimes forget to. But yeah, like rearranging it before you plug it in.
Yeah, I mean, like, that takes practice and stuff like that. Um, but yeah.
In a related experiment, leg extensor power was used to assess muscular fitness. Subjects were in a seated position, and a single explosive lower limb extension accelerated a flywheel from rest. Whatever. I don't even think it matters. Like the results of extension. Okay, they replied below. And yes, how do these results relate to the grip strength result in the passage? Basically, they're just testing whether or not we know like correlation. So yeah. Uh I was just a little, I guess, confused between like inverse versus negative correlation.
Oh, okay. That's a good question. So, um, your how should I put this? Um, okay, let's see. Well, okay. Inverse could be this. So, like, usually in psych soc, they would say like negative or positive. Everything else, though, we think of it as direct or inverse. So direct is just going to be positive, and inverse is just going to be negative, like equating those. So, but the real thing here is significant versus slight, right?
Mhm.
And, you know, um, yeah. So yeah, what first let's figure out if it's going to be direct or inverse.
Inverse.
Why?
Because as the age goes up, the power goes down.
Now, is that what the question's asking you?
Grip strength.
The grip strength results in the passage.
Oh wow.
Yeah, MCAT's never just going to be that straightforward, and it's always going to hinge on the nuances in language. That's why reading is so important for the MCAT.
So it's just direct.
Yeah,
Jesus. Yeah.
yeah. And now whether it's significant or slight, um, I guess we kind of have some help here because there's only one choice with direct, but whether it's slight or significant would be like the strength of the I guess like the strength of the correlation. So like if it was like you know like I don't know, let's say that you had some values like this, and then this is your line of best fit or whatever. It's not really that strong compared to if you had something like this,
Mhm.
where it's stronger. Because it's almost like you take, like, when you take like, let's say these are your actual values, and your line of best fit is here. The distance between these, you know, data points, like the further the distance is from the data points, the weaker the correlation. And the closer they are, the better, the closer they are. So yeah,
Mhm.
this would be a significant one because it doesn't seem to be like these ones are pretty far, but for the most part, they're pretty much lining up with the line of best fit. But yeah, this is like honestly, this is like what they're doing. They're like, okay, they're putting in like leg extensor and pre-meds are going to be like what I don't what's that? They're going to be like lower limb extension and then flywheel. They're going to be like what? From rest, all this stuff. And
Yeah.
pre-meds like to minimize the amount of reading, but you want to not fall prey to that. You want to make sure you do your reading.
Yeah. Probably like Altius though, because like there's a lot of analysis and like graphics or like data interpretation and stuff.
Yep.
Like if this was Blueprint, it would just be asking you to like calculate power 600 times, and then like how that relates to like
Yeah, yeah,
the
yeah.
work.
Yeah,
So
yeah.
it's at least it's getting me more prepared. Okay. So this is the last one. Suppose the dynamometer is held in a hand with an unsupported arm. In which situation would the dynamometer weight exert the most torque on the shoulder?
Hmm. Okay.
So yeah, I mean torque is one of my probably worst topics out of all the physics ones.
Okay.
So
So, so tell me in your own words, I guess, what your understanding of torque is.
basically like I know there's rotational forces and like I forgot what the other name
So
is here.
our
But
so work formula is FD cos theta. That cosine means that, well, yeah, what does that cosine mean? Significance of the cosine value here.
um that basically the it has to be perpendicular.
What's cosine of
Oh wait, no, parallel.
Mhm. So cosine at what angle is maximized?
Um, 90.
So, okay, so this is your sine, this is your so sine, cosine, and here is 90 degrees. So, and then here is 0 degrees. So the cosine at 0 is 1, at 90 is 0. Sine, so I'll write it like this. So cosine of, let's say, 0 to 90, and then sine 0 to 90. So that the cosine at 0 is 1. At 90, it's 0. Sine at 0 is 0. At 90, it's 1. So, in other words, uh, if you have a cosine term and the angle is not 0, it's going to be a value less than 1. And if we're multiplying, like, let's say FD by a value less than 1, it lowers that overall value, right? That overall product.
Yeah.
So in order to maximize that, we need the angle to be 0 in order for the cosine term to be 1. So we can write the work formula like this with this subscript meaning parallel. Okay.
Yeah.
Now, the reason it's torque, we're talking about torque. The reason I'm talking about work here is because torque is essentially the same thing, except with a sine term. The sine term means that it's maximized, aka 1, at an angle of 90 degrees. Okay?
Mhm.
So I could rewrite this to say with this subscript meaning perpendicular. Okay?
Yeah.
So this also means that if you're doing if you're doing torque, you're not doing work. If you're doing work, you're not doing torque. Okay? Now, let me give you a real life example. So, and I'm going to ask you what for each scenario, what's the work amount, what's the torque amount, and your answer choices would be like 0 or greater than 0. So, when you open a door, a regular door,
Use torque being done.
uh-huh. So, a not a greater than 0 amount of torque and a 0 amount of work, right?
Yeah.
Okay. And that's because, if your hinge is here and your doorknob is here and you open it or close it, it would rotate, but also the force that you're applying is perpendicular to the length of that door, right?
Mhm.
Okay. What about a sliding door?
Well, I guess there's work.
There's work, right? And no torque, right?
Yeah.
Because the force is in the same direction as the door that's moving, right?
Mhm.
Okay, good. So work requires the angle between the force and the distance to be the same. Well, when I say the same, I mean 0. Um, and torque is when the angle between the force and the distance is 90 degrees. So if you're turning a page on your notebook, are you doing torque or are you doing work?
Torque.
Good. Okay. So this is saying diameter is held in a hand with an unsupported arm. So I guess just one hand. What situation would exert the most torque on the shoulder? So let's start with A.
The most torque.
Okay.
Okay. Okay. Um, Arm hanging vertically on bend.
Okay.
So that's just like the arm hang like droop down.
Well, it says vertically, right?
Yeah.
Oh, I guess when you say droop down, that's what you mean.
Yeah. Or like all the way up.
Yeah, like either, well, I guess you can't see me, but down like that, right? Or yeah, over. But I guess it says hanging, so it's more down. But
Yeah.
so think about
Okay.
that, right? So let's say this is the hand. So this is the force of gravity, and this is the, distance or length of the hand, and you know,
Okay.
they're parallel, right?
Right.
So is there any torque happening here?
No, it's work.
Good. All right. What about B?
Upper arm hanging vertically, lower arm bent at 90. Um, um, okay, lower arm.
I think it would be like this. Oh wait, upper arm hanging vertically. Oh, like that. So like that.
Yeah. So, okay, that's the most amount of torque.
So yeah. So okay. The if the length so part of the length is here and the force of gravity is here. So there is some torque happening here. Um, so okay.
Arm extended horizontally unbent.
Okay.
Like that. Like that.
Hmm.
My question though is like, how is C different from A? Well, yeah, but like, I mean, wouldn't C technically be having torque? It's like a 90 degree from your body.
Yep.
So it would.
Hmm.
Interesting. So it's between B and C. I mean, the upper arm extended horizontally, lower arm bent downward. Upper arm extended horizontally. That's also torque.
Upper arm extended horizontally, lower arm bent downward.
Okay.
So this is your force, and this is your distance. They're parallel, right?
The force has to be parallel to the distance.
In this case, for the lower arm, right?
Okay.
Here, I'll draw each of these one more time. So arm, entire arm hanging vertically. Um, Upper arm hanging vertically, lower arm bent at 90. Arm extended horizontally unbent, and then upper arm extended horizontally, lower arm bent. And
Yep.
this is your force here, force here, force here, force here. This is your, distance. Here, it's like distance over two here, distance over two here. This is distance. This is distance over two, distance over two. I'm saying distance over two because I'm separating the upper arm from the lower arm.
Mhm.
So, do these drawings make sense?
Yeah.
Okay.
Um, what's between B and C? I guess C,
Yeah, why?
because there's a full distance.
Yeah, it's a greater distance, right? And because so basically, so this one, the force is parallel to the distance, so this torque is zero. Okay. This one, there is some torque here. Let me use blue. Here, there's torque. So there's a greater than zero amount of torque. But this part is not involved in the torque. So, it's not as high as it can be. Then this over here, this part over here is not producing torque, but this part is. So this could still be a torque greater than zero, but but here you have the larger D value or R value, right? So that's going to produce the largest torque.
Mhm. Okay.
Mhm.
Also, do you know next time you're gonna upload like videos?
Oh yeah, I like finally like edited um a bunch of them, and uh they are on a schedule, so like one
Mm,
will be released each day.
okay.
So that means that the well, episode 25 just dropped.
Oh yeah.
Yeah. And then
Okay.
tomorrow it'll be 26, after that 27, after that 28, 29, etc. Um, if you want something, sooner, you can let me know. I can upload it, and put it as unlisted. Um,
Mhm.
yeah,
Okay. But then the ones in queue right now are like my sessions, right?
correct. So
Okay.
episode 25 through 34.
Got it. Got it. Okay.
Yep.
Understood. All right. Do you have a person at 7 o'clock?
No.
Okay. Then here, we'll do this passage, but we could cancel the Monday session.
Oh, okay.
Yeah, so just remove me for that because I think by Monday, like I'm not really gonna have anything new, that I want to discuss.
Okay.
Because we could just get both things, both passages done today. Okay.
Um, so okay. Oh, so
Yeah.
you need to do this passage. Uh,
So also to recap, torque is basically perpendicular and then work is parallel.
Yeah, so you can also think of it as is this type of thing going to produce a pushing or a pulling or a rotation? If
Mhm.
it's pushing or pulling, it's going to be work. If it's causing a rotation, it'll be torque.
Yeah.
Hmm.
All right.
Okay.
Glycogen phosphorylase is a dimeric enzyme that catalyzes the release of glucose from glycogen.
Okay.
Reaction one.
What's a phosphorylase?
Phosphorylase, it adds a it's a transferase. It adds an ATP, but it can't remove the ATP like a kinase can.
Yeah. So when you say ATP, you mean a phosphate group.
I mean a phosphate, yeah.
Okay.
That
What's glycogen?
glycogen is stored form of glucose. It's
So
usually stored in the liver.
it's a polymer of glucose, right?
Polymer of glucose, yeah, and there's the alpha 1 4 and alpha 1 6 bonds.
How are those? Yeah, tell me, like, what's the difference between them? Or like,
The alpha 1 6 is branched, the
yep.
alpha 1 4 is like normal, and the whole point of it is so that like you increase, I guess, surface area or whatever, so they're
Oh.
more compact.
So the branches increase the surface area, making it better, more soluble, right?
Yeah.
Okay, good. And okay, they're saying, oh, and then this enzyme, does it have a quaternary structure?
I mean, yeah, because it's a dimer.
Good. Okay. And it catalyzes the release of glucose from glycogen. All right.
Yeah. GP catalyzes hydrolysis of linear glycogen molecules with alpha 1 4 glycosidic linkages only. Okay. Hydrolysis, it adds the water, so it breaks it up. And then alpha 1 4 glycosidic linkages
Okay.
only. When alpha 1 6 glycosidic linkages is encountered, branching enzyme is required for hydrolysis can proceed.
Okay. And so we see reaction one. What can you describe here?
Um, so like a glycogen is one less glucose because the glucose gets cleaved off and there's a phosphate on the glucose.
Okay. So we're taking glycogen with N number of whatever and adding inorganic phosphate, and then we end up with glycogen N minus one, and the glucose that's released is going to be yeah, phosphorylated. Good.
The reaction one occurs in liver and muscle tissues to regulate blood glucose levels and supply energy for skeletal muscle contraction. GP active site contains a pyridoxal phosphate, covalently bound to a lysine residue inside a ligand pocket.
What can you tell me about lysine?
It's basic, has a positive charge.
Uh-huh. And okay.
Yeah. Phosphate group on PLP stabilizes the carbocation intermediate during the cleavage reaction shown in figure 1.
So tell me how a phosphate group can stabilize a carbocation intermediate.
Phosphate is negative, the carbocation is positive.
Mm-hmm. So it can it behave as a something something.
Nucleus. I mean, hold on. So yeah, the phosphate can behave as nucleophile.
Oh, sorry, I meant it can be described as a something something group.
Electron donating group.
Good.
Okay. GP is
So
regulated. Hmm?
yeah, so okay, so now we see this figure
Yeah.
and like on the test when you're doing this timed 15 seconds, no longer than that to get the gist of what's happening. If it takes longer, move on. And, if they ask you to go back to it, you can go back to it. But yeah, spend like 15 seconds trying to see what's happening. So, what do you see happening?
There's a leaving group. The leaving group leaves, and there's a positive charge. And yeah, so it comes off, and then I don't know. I guess the HOR then leaves, and
Mhm.
then it comes back, goes back on to the glucose.
Mhm. Okay.
Yeah. GP is regulated through phosphorylation of a serine 14 active site residue and through binding of allosteric effectors away from the active site. GP is allosterically activated by AMP in muscle cells and allosterically inhibited by glucose in liver cells. Phosphorylation of GP is regulated by epinephrine and insulin levels in muscle cells, and by glucagon, epinephrine, and insulin levels in liver cells.
What does insulin do?
Decreases blood glucose levels,
All right. But what happens with that blood glucose?
gets put into glycogen stores.
Yeah, good. Glucagon would then, so this reaction, so what is this? Oh, I guess like the name of this kind of reaction. Um,
Glycogen phosphorylase.
I guess I just mean so glycogenolysis,
Yeah, that's
breakdown
just
of
like
glycogen.
breakdown. Yeah,
So um that would be something glucagon would do, right?
yeah.
Okay. Anything else on this passage? Like underneath?
No,
All right, cool. Um, one last thing. So so you know how like a peptide bond is an amide? Um,
yeah.
what functional group is a glycosidic bond?
What do you mean, like in ether?
Um, so like here.
Uh, like what is that? Glycoside? I don't know. Um. Oh, yeah, yeah, yeah. Don't worry. I know it. I know it. I know it. I know it. I know what it is. It's a hemiacetal.
So Um, if it was like this with an OH, aka like in a monosaccharide, it would be a hemiacetal.
Okay.
But when it forms a bond, the OH is now another OR
So just acetal. Okay.
acetal, yeah. And
Okay.
they like to ask questions about is this a reducing sugar or yeah, reducing sugar or not?
Yeah.
So an acetal or a ketal cannot be reduced. Sorry,
Mhm.
cannot be oxidized, meaning they cannot be reducing sugars, but a monosaccharide or the very end of a polysaccharide can be a reducing sugar. So, okay. So let's see. Okay, which of the molecules shown below is cleaved by GP?
Yeah, I think this one I have right, I think. But so GP, it's alpha 1 4 glycosidic linkages only between glucose. So like C is out. Um, and then like here, the structure of glucose, this is like wait, this is not it. This is 1, 2. This is just not even how glucose looks like.
Yeah.
So I put A was out and then B was out.
Hmm.
One,
Yep.
1, 2, 3, 4.
Hmm.
So yeah, it should be that.
Good.
Yeah. Um, okay. So now this, yeah, I wasn't sure about. Leucine to aspartate, whatever, asp mutation along the GP dimer interface most likely. So I was just a little confused on how to approach this.
So before we look at that, what happens here?
Leucine is leucine just has no charge, so 0.
Okay.
And then asparagine is also has no charge.
So is that an asparagine?
Asparagine. Asparagine. Wait, yeah.
Wouldn't that be this?
Oh wait, aspartic acid. Sorry,
Yep.
aspartic, aspartic acid
So we're going from uncharged to
to
negative
negative. Yeah,
charge.
yeah.
Okay.
Okay. On the exam, though, I remember thinking it was negative. Uh,
Mhm.
so yeah, along the dimer interface would most likely. I was just confused about the like dimer interface thing. Um, so because yeah, so it goes from 0 to negative. Um, along the dimer interface. So the phosphate PO group on PLP stabilized carbocation intermediate during cleavage reaction. I don't know. I was just a little clueless. Like I didn't know where to look for this because they also spoke about an active site here. Allosteric Cofactor with an active site. Then here they spoke about the lysine residue and the ligand pocket.
Uh, we can think about this just, I guess, purely conceptually, right? So, a dimer would involve like two, I guess, like monom polypeptide monomers to bond with one another.
Yeah.
right? And if you have leucine, something that's, not charged, it can come close together. But if you have two negatively charged things, they would repel one another,
Hmm.
wouldn't they?
Yeah.
And if they repel one another, that would make it more difficult for them to bond and therefore form a dimer, right?
Okay. Yeah.
So, um, I'm pretty sure even if they said like instead of aspartic acid, like lysine or something, it would still be the same answer because when you have charged things, you know, like charges will repel each other. Yeah.
So why would it not be B? Because the answer is A.
hmm Yeah. We don't have any information that would tell us if it's going to be uh permanently active or inactive. I mean, they did say that they did say that there are certain things in the active site. Okay, they said allosterically activated by AMP, allosterically inhibited by glucose, and allosteric effectors and stuff like that. Um, yeah, I guess nothing here can really tell us if it's going to be, you know, active, like turned into an inactive or active state, and certainly not anything permanently doing that. So yeah, so I think B and C just there's nothing in the passage to suggest that that would happen from this mutation.
Okay.
Uh, I think this is just more of like a yeah, like a almost well, I want to say pseudo discrete, but just the idea of like a dimer. Um, you know, yeah.
Okay.
Well, to go more into that, you can also think of how tertiary structure is predominantly formed by hydrophobic interactions,
Mhm.
right? And leucine is a hydrophobic, you know, amino acid, so that can contribute to that quaternary structure forming. Uh, but yeah, if you have charged like charges, then they're going to repel one another.
Okay.
Okay.
The alpha 1,4 linkage between glucose molecules and glycogen is cleaved via what mechanism?
Oh, I see. I think you were talking about this before.
Hmm. Well, it's not E2 or U1, I feel like.
Correct. Because if there was, you would. So, okay, so we have this thing attached, and then it breaks off, and this is our carbocation intermediate, and then it attaches back on, or like, the new thing attaches back on. So it's a substitution reaction, definitely. If it was an elimination, it would be like a double bond or something.
Yeah. I mean, I guess here I wasn't sure if they like, I guess, yeah, they were referring to this, but I wasn't totally 100% sure they were referring to the picture. Well, now if I know that it's C, obviously, because there's a carbocation intermediate.
So they're saying glycogen cleaved via which mechanism, and this says mechanism of glycogen phosphorylase, and here they say glycogen phosphorylase catalyzes, the cleavage of, you know, uh, the molecules in the glycogen.
Okay. Yeah. All right. Next. In reaction one, PLP phosphate group. Okay. Uh, it acts as what? So, PLP phosphate. Reaction one.
Oh, I was looking at the. Sorry, yeah.
I guess they're according to the equation, right?
Well, okay. So yeah, so they're talking about so the reaction one is showing us the overall kind of thing of this glycogenolysis thing. But figure two shows us like the mechanism because reaction one doesn't, give us anything about PLP or anything like that, right? So we're still going to be really using figure one here. And yeah, we want to know what the so like, this is our PLP, right? This is our uh whatever glucose, and there's like a hydrogen bond happening here, and okay, and then this breaks off, and this connects onto it. um PLP phosphate group. Oh, wait a second, this gets attached to that, right? Do you see that this and this are distinct, right?
Yeah, I just saw that.
Because this is a dotted line, which indicates like hydrogen bond rather than like a covalent bond.
Okay.
And but this is a covalent bond, right?
Yeah, then it's A. I didn't catch that.
Yeah.
I put that it's a nucleophile.
Then
Okay.
yeah.
Right, so it's A. Why wouldn't it be a nucleophile though?
Yeah, I was thinking about that because that's what seems to happen here. Let's see.
It says PLP does not that PLP phosphate does not directly interact with the glycogen, which would be necessary for either for this to be correct. What?
Oh, I guess that what they're showing us here is just a glucose.
Hmm, okay.
Yeah, I guess it may appear like it does this nucleophilic attack in that like second step or whatever. Um, and reaction one says that I mean, like, okay, like, I guess, so we can see that it is donating a proton first, and then it may do a nucleophilic attack, but, I think that, it's not like I guess like the first thing that it does is it donates a proton, so we can choose the most direct answer.
Yeah.
So yeah.
Okay.
All right. Reaction velocity in the absence of all allosteric effectors, so no, like, whatever, glucose or insulin or any of that stuff. Oh, and then if glucose is added, the midpoint of the curve, shift left, unchanged, shift down, shift right. Um, we could eliminate one choice already, right?
See.
Mm-hmm. Shouldn't shift downward. Okay, and then they said that glucose causes allosteric inhibition, right? So, uh, if glucose causes allosteric inhibition, we can then also get rid of B because something will have to change. Now we want to ask ourselves, um, a leftward shift or a rightward shift, like which would make it better at what it's doing, and which would make it worse at what it's doing, I guess.
Um, I would think, well, if glucose is inhibiting it,
Yeah.
we would need more of the substrate for it to do something.
Yep. And that would
So
be,
it
yeah,
shifts right.
exactly. Like for any of these, right? It's like even with like the Bohr effect, if you shift to the right, it means in order to have the same reaction velocity, you need a higher amount of substrate.
Okay.
So, yeah, so this will be true for like, all like kind of sigmoidal curves in which you have a shift, like in hemoglobin and the Bohr effect and stuff. So, yep,
Mhm.
that's it basically.
Okay.
Yep. So, uh, yeah, so that figure one was pretty confusing, but they didn't ask us much about it, right? So we were able to still kind of do that. But awesome. So yeah, you're taking your next test
Right. Next Friday.
next Friday. Okay. And I will see you on
Next Wednesday.
yes at 6 p.m. Eastern.
And what was the call?
Oh yeah.
That's 6:15.
Yeah, it's an hour.
Yes.
So 90 minutes.
Okay.
All
All right.
right.
I'll see
Awesome.
you.
Have a good weekend. All right. Take